Hi guys, this week we will continue sampling distribution topic. So we will see sampling distribution related with t-distribution and also x-distribution. Then we will combine everything actually. Mostly we will deal with sampling distribution. Sampling distribution of a statistic which is generated from normal distribution. Okay, so sampling distribution related with t-distribution, student t-distribution. Where we are using t-distribution mostly for testing the population mean. If you remember from stat 156, population mean. Okay, so to make inferences about unknown parameters, we are using statistics. So to make inferences about unknown parameters, we are using statistics. Statistics like the sample mean instead of mu, and sample variance instead of sigma square. For other distributions, we can use different parameters, different statistics to estimate unknown parameters. So mostly for normal we have only two parameters. If you know mu and sigma square, we totally characterize the distribution. So these are the most important ones for many applications. However, the distribution of x bar also depends on the parameters of sigma square. So when we consider the distribution of the sampling distribution of x bar, if you remember, that is from normal distribution, x bar distributed as some distribution, mostly normal, if we use central limit theorem, or if the random sample coming from normal distribution with mu and sigma square over n. So we have two parameters actually to describe the sampling distribution of x bar. So this makes it impossible to use x bar for certain types of statistical procedures concerning the mean when sigma square is unknown. So if sigma square is unknown, it is difficult to make inference on mu. So what we are doing most of the time, instead of sigma square, we replace it by s square. But then the sampling distribution of x bar changing when we do this replacement. So let's consider a simple example where we are using t-distribution actually. Let's say we have a principal of a school. Principal at a certain school, and he claims that, or she claims that, the students claims that students of his school, very smart, are above intelligence. If we say that the average, so how we are measuring intelligence by IQ score, let's say average IQ is 100, then actually he claims that in the alternative hypothesis average is 100, but his students is above average. So here we need to we need to do this test and then be sure that his claim is correct or not. So if here sigma is known, and let's say we collect actually n equals 50 in case, okay, then the test statistic that we will use is z. Here we are using x bar minus mu. The z is capital also. Okay, sigma over square root of n, and we know that this is standard normally distributed if we have a normally distributed sample. Then by checking our scores that we obtain actually, so let's say we have a normal distributed distribution random sample, mu is 100, and let's say this is our alpha critical value. So if our sample point is in the critical region, then we reject the null hypothesis. Okay, reject A0. So we are converting this to a standard normal where we have 0 mean standard deviation 1 or variance 1, let's say, and this score, the above value, is known as z sub alpha. Whatever that score is, again this probability is alpha, again this part is the reject A0 part. But if sigma is unknown, we replace sigma by s, right? So then what is the distribution? But now what is the distribution of x bar minus mu divided by s over square root of n? So this is the random variable, capital S. Okay, so we don't know the distribution of that. So we have to derive the distribution to be able to do this testing. Okay, so we have a theorem. If we have a standard normal distributed random variable z, and let's say we have another random variable v, and it had chi-square distributed with new degrees of freedom, and assumptions, if z and v are independent from each other, then the distribution of t equals z, these are all capital, and in square root v over nu, okay, is student t distributed with new degrees of freedom, and denoted by t distributed as t, okay, with degrees of freedom nu. So we need to use t distribution to be able to decide the critical region. Instead of z, we have to replace this z by t in that case. Okay, so basically you know where the students came from. So we have just students t. Why we are not just saying t but students t? Students t. Do you remember or do you know where it has come from? So actually it is the t distribution is discovered by Gossett actually in 1908. Okay, and he discovered this distribution when he was working at the Irish brewery Guinness. You may know this brand, and his paper published in a Biometrica under the name Student. Actually, he wanted to publish it as t distribution, but Guinness didn't approve this due to protect the trade secrets. They didn't want other brewery brands know that they hire a statistician. So because of that, Guinness didn't want to competitors to know about the about this actually. So, but he said that this is very important discovery. So he wanted other people to know how to deal with small sample cases, especially when they need to deal with this testing procedure. So he sent his work under the name Student. So it is known as student T distribution. So he didn't publish this work as his name as Gossett, but as student. Okay, so find my notes, so they mixed a little bit. Sorry about that. Where are my notes? Okay, so this is okay. Okay, so he published his T statistic under the name student. Okay, so let's try to prove it. Okay, so we need to use transformation techniques to be able to prove it actually. So here's what we know. We know that Z is standard normal and V is chi-square distributed random variable with new degrees of freedom, and we know that they are independent. Okay, so we have to use the known information. What we are doing, then we need to show the distribution, or we need to find the distribution of Z over V over nu. So what is the distribution of this? So we have to use, this is the basic transformation problem that we have to solve. So what we need to use, okay, so we have Z and V, we know the distribution. So from that we need to find distribution, marginal distribution of T. So we have to consider first the joint PDF of Z and V, okay, and so let's write it. So because they are independent, so we have to write it as a multiplication, okay. So we have a standard normal PDF and chi-square PDF. So this is V, this is nu, minus 1 e to the minus V over 2. Okay, and the range of Z is from minus infinity to infinity, and range of V is positive because it's chi-square. Okay, so then consider transformation. And where we define our T, which is Z over V over nu in square root, and then let's say U equals to V. Okay, so from here we need to define our Z and T scores. Z equals, T equals, not T, V, sorry, V equals, so it is U, and Z equals to T times U over nu. Okay, and then from here again, since we are using transformation, we are changing the dimensions. So to make everything in the same dimension, we need to use this adjustment, Jacobian adjustment. Nu, take the derivative of Z with respect to T and also U, nu, and 0, 1. So basically U over nu will be our Jacobian. Then the joint PDF of T and U can be found as TU. Okay, so instead of Z we replace this quantity T over T times square root of U over nu, and instead of V we replace it by U and multiply the joint PDF by the Jacobian. Okay, so then we have square root 2p, and then we have e to the minus t square u over t 2 nu, and then the gamma function 2 to the nu over 2, u to the nu over 2 minus 1, e to the minus u over 2, and multiply with the Jacobian. Okay, so here's our t is from minus infinity to infinity, our u is positive. Okay, so then we can find the marginal distribution. So this is our aim actually. Marginal PDF of t is found by the joint PDF actually. So integrating joint PDF and give all the information related to u there and get the result. So after that you will end up with one PDF. which is this one, gamma nu plus 1 over 2 and nu over 2. Then we have nu pi, and we have 1 plus t squared over nu, and to the power minus nu plus 1 over 2. Okay, and the range of t is from minus infinity to infinity. Okay, and this PDF is known as student TPDF. PDF of students T with new degrees of freedom. Okay, so when we go back to our problem, basically, so go back to our problem. So we have z equals x bar minus mu divided by sigma over square root of n, and v equals to n minus 1 s squared over sigma squared. And we know that this is standard normal distributed, and this has chi-square distributed with n minus 1 degrees of freedom. We already proved that, and we know that these two are independent. We all prove all these things. Then let's say we have t, which is z over v over degrees of freedom. Okay, so we have x bar minus mu sigma over square root of n divided by, in parentheses in square root, n minus 1 s squared over sigma squared divided by degrees of freedom. Okay, here's the sigma terms will cancel out, this n minus 1 terms will cancel out, and we have t as x bar minus mu s over square root of n, and this has t distribution with n minus 1 degrees of freedom. Okay, so actually we are not directly replacing sigma by s, but doing this, considering this ratio of these two, where we generate t distribution, gives us the form actually. So here it seems like we are replacing sigma by s, but actually we are not replacing it. We are just getting the ratio of two statistics, which one of them is standard normal, the other one is the chi-square distributed random variable. So we use the how we generate t distribution from that actually. Okay, and when n is when our sample size is greater than or equal to 30, by central limit theorem, this t is almost like normal distributed approximately for large n. Okay, so t distribution is symmetric, so it is a symmetric distribution, and expected value of t is 0, so it's symmetric around its mean 0. And when we consider variance of t, it is n over n minus 2. So here the sample size should be greater than or equal to, or actually just greater than 2, not equality, because then the variance will not be found in that case. So for smaller n, for smaller degrees of freedom actually, distribution is flatter, platykurtic type with thick tails. So and when nu equals to 1, t is actually a Cauchy distributed random variable with 1 and 0. So the variance is not exists actually. So you know, for Cauchy distribution none of the moments exist. So from the variance formula you already can catch that. So t is related with Cauchy distribution. When nu is 1, we directly have a Cauchy distribution. Okay, so let me stop here. I will continue with this sampling distribution related with F distribution. Okay, I hope I can do that.